In our journey through the story of the universe, we arrive at the oldest light we can see. The cosmic microwave background, or CMB. Often called the baby picture of the cosmos, it is the faint afterglow of the Big Bang itself, permeating every direction of the sky. Its discovery was accidental. In 1965, Arno Penzias and Robert Wilson detected a persistent noise in their radio antenna that they couldn't explain. It turned out to be the thermal radiation left over from the time of recombination. It is the most perfect blackbody spectrum ever observed in nature. About 380,000 years after the Big Bang, the universe cooled enough for neutral atoms to form, allowing photons to travel freely for the first time. While it appears uniform, precise measurements reveal tiny temperature fluctuations, anisotropies of just 1 part in 100,000. These microscopic fluctuations are crucial. They represent the seeds of all future cosmic structure, the density variations where matter would eventually clump. Gravity amplified these tiny overdensities over billions of years, pulling matter together to form the first stars and galaxies. The CMB provides the strongest evidence for the Big Bang theory and is a pillar of the lambda-CDM standard model of cosmology. By analyzing the angular power spectrum of these fluctuations, we can determine the precise composition of our universe. The data indicates that the geometry of our universe is spatially flat to within a very small margin of error. When we look at the CMB, we are looking at the surface of last scattering, the edge of the observable universe in time. Cosmologists are now hunting for B-mode polarization in the CMB, which could be the smoking gun for cosmic inflation. These patterns would be the imprint of primordial gravitational waves generated during the fraction of a second of exponential expansion. The study of the CMB transformed cosmology from a speculative field into a precision science. We must also account for effects like the Sachs-Wolf effect, where photons lose energy climbing out of gravitational potentials. The peaks in the CMB power spectrum correspond to baryon acoustic oscillations, sound waves propagating through the early plasma. Yet mysteries remain, such as the cold spot, a region unusually large and cold that challenges our standard statistical models. As CMB photons travel to us, they interact with hot gas in galaxy clusters, known as the Sunyaev-Zeldovich effect. This allows us to detect massive galaxy clusters and map the large-scale structure of the universe using the background light itself. From a serendipitous noise in a radio antenna to the most detailed map of our origins, the CMB tells us where we came from. It is the thermal remnant of creation, a snapshot of the infant universe that determines the fate of everything we see today. Thanks for watching this chapter of our cosmic story.